overtired.
Same.
I cannot get my kids to sleep at night.
That sounds like a...
Yes, they seem to like be thinking that they're like 6 months old and they have to be up at 2 o'clock in the morning, and I don't understand.
That is 6.
All right.
Yeah, that's...
All right, today we're going to continue on through section 5.6. And 5.6 is only a tiny bit more new material and then just more exercise in doing this stuff. Remember, last time we met, we did that method of substitution thing. I'll be honest, method of substitution is pretty much like one of the biggest tools for solving integrals. Turns out, tons and tons of integrals are solvable that way. And we're just adding another tool or another set of rules or whatever that you'll be combining with substitution. And that is, we're going to be talking about the integrals of logs and exponents today. And it's not going to be all that big of a deal. I mean, if you think about it, the exponential function, e to the x, was in many ways the easiest one when we did derivatives a chapter or two ago. Because remember, the derivative of e to the x is e to the x. In fact, that is one of the ways you can define the derivative, the exponential function. It's the only function where this is possible. And we've also learned from the fundamental theorem of calculus that derivatives and integrals are kind of the opposite of each other. They are inverse functions of each other. So whatever's, so if we had that the derivative of e to the x was e to the x, well, what would the integral of e to the x be? It's just e to the x. Okay, now if it's an indefinite integral, it's e to the x plus some constant. Any constant would work. Or if it's a definite integral, like let's say we had some numbers here, then it would be e to the x evaluated at b and a, or e to the b minus e to the a. And we can apply, excuse me, some of those nifty exponent type rules that we learned in back in like pre-calculus, and start, well, that's the same thing as e to the b, well, I don't want to go there, okay? Exponent and log rules. So this is not going to be all that hard. Now, they're not going to give you one that simple in the class, but we can start combining it with stuff like our substitution method. So like, for example, just as a really slick little thing, let's just look at example 5.37 on that first page of this section here. It says, what if you were talking about the integral of e to the negative x dx? Now that's not a rule that we have done yet, but we can do a substitution here. Now we can try different substitutions here, but the one that I think is going to work best is just say u equals negative x. Remember, we want to get this into a form where when we have that u in there, now it's an easy integral. Well, if u was just negative x, this will just be e to the u. That sounds easy. So then du dx, the derivative of u with respect to x, is just negative 1. Or another way to write that would be to move the dx over to the other side. So our du equals negative dx. So let's see how we're going to rebuild this thing then in terms of u. E to the, well, negative x is u. Alright, that leaves us dx. But dx is the same thing as negative du. I'll put the negative out in front just to simplify things a little bit. Excuse me. Well, now we have an easy form. Alright, so that can just be negative e to the u plus c. Or we can do our substitution back in there, negative e to the negative x plus c. Yeah, I put that back in there. Substitution really is the grandest of the tricks when it comes to this stuff. Alright, let's see what else we can do. How about another one of those guys? Hey, I wanted to show you something, by the way. So if the integral of e to the x dx equals e to the x plus c, there's actually a more general way to write this. I only have a tendency to think it happens in one of the problems here. What if it wasn't e? What if it was any old number? Let's just say a to the x dx. Where a could be base 10 or it could be anything. Well, it turns out it's just a to the x divided by the natural log of a. Natural log of a, though, I mean, if we had been using e instead of there, that would have been this, the natural log of e, which is just 1. So that would have all just gone away. So that's explained there in it's Rule 5.21 on that first page of section 5.6. Anyway, then your book just does lots and lots of examples of exponential and so on, doing the method of substitution, which doesn't really strike me as the best use of our time up here in front versus you guys doing those problems. So, I mean, there's lots of examples or whatever. I do want to point you out to example 540 on page 597, where they're actually doing it happens to be a story problem involving a price-demand equation. Okay, for various reasons, we're not going to do stuff like that. Same with like, there's another one that's like growth of bacteria in a culture. Well, okay, you guys know from classes like pre-calculus that exponentials are often about growth. Like the growth of money in a bank account, or the growth of bacteria in a colony, or something like that. Okay, I think the book is treating it like that's something you've never seen before. Okay, like ooh la la, look what you can do with it. Okay, you know that already. You know that these exponentials, that's often what we do with them, is we're using them to talk about growth. So I'm not really sure that a bunch of problems where we're just doing the same thing, except instead of it being x, it's n for number of ants in the colony, strikes me as the most exciting. I mean, but I'd rather you get exercises on doing this than that particular thing. Anyway, so there's a whole mess of these guys. They're just examples there. Let's actually do example 541. That's on page, I don't know, 598. I only like this particular one because it's a definite integral. I want to just exercise that a little bit real quick. So like if we had the integral, I think it's the integral from 1 to 2 of e to the quantity 1 minus x dx. Okay. Again, more just because I want to reiterate what a definite integral is. Remember, like another way to write this would be to say like that means x equals 1 and x equals 2. In other words, like from x equals 1 to x equals 2, we have this function doing something here. We want this area underneath here. Alright, now again, this is going to be a method of substitution problem. We want to get this thing into a form that looks easier. Well, if this was e to the u, that would be about as easy as it's going to get. So I think, in this case, u equals 1 minus x would be darn helpful. If that's going to be our darn helpful thing, the derivative of that u with respect to x would just be negative 1. Or du equals negative dx. Another way to write that would be negative du equals dx. We'll see what we need here. So let's put this thing together. Okay, let's forget about the limits of the integrals here for a second here. Just say the integral of e to the u. Okay, what's left? This is e to the u. All we have left is the dx, which is negative du. So here's du, down with the negative sign out in front. Alright, well that's easy. That would be then negative e to the u plus c. Well, actually, though, we want to do a definite integral. That would be... Now, remember, there's two different ways to do this. We could either come up with the new limits of the integral over here. Previously, x was equal to 1. If x is equal to 1, u is equal to 0. X was equal to 2, then u is equal to negative 1. We could then put those in here. Negative 1, 0 equals negative e to the negative 1 minus e to the 0. That would be one way to evaluate it and then simplify. Or we could go the other way around and say we got e to the negative u, which would be the same thing as e to the negative 1, what was it? U is equal to 1 minus x. And then evaluate this whole thing from x equals 1 to x equals 2. Either way would be fine. And you'll in fact get the same answer both ways. In a later calculus course, you find out that there's pros and cons to both of those ways. And certain kind of problems are going to be better one way than the other. But in this class, it actually, either of those techniques, both of which you got lots of exercise on using your assignment from Tuesday, would be fine. And of course, this all has all kinds of simplification going on here, right? Negative 1 over e minus 1. 1 minus 1 over e. I mean, you'd have to go simplify as you need to. All right. Now, this is about logs and exponentials. Boy, for as easy as the integral and the derivative of e to the x are, sure seems like log should be easy, but as we saw back in chapter 4 or whatever that was, the derivative of the natural log is not a simple, well, it wasn't so simple. Do you happen to remember what it was? Was the derivative of natural log 1 over x? Yeah, I think that's right. I always get confused as to whether it's 1 over x or if it's x plus 1 over x. I think it's 1 over x. All right. That's odd. On the other hand, it does tell us something interesting. The integral of 1 over x dx, I mean, since these two are opposite each other, is the log. Integral of 1 over x is the log. Now, there's a little bit of a problem here. Well, first off, there's a problem because it's got to be plus c. I'm writing this here as an indefinite integral. But there's actually a bigger problem. I don't see any reason here, looking at the left-hand side of the equation, why x couldn't be a negative number. I mean, I don't see any reason why I couldn't do the integral of 1 over x dx from something like x equals negative 5 to say 0. Well, I can't see why it couldn't be 0, right? This would blow up. Maybe, let's say that, just to keep ourselves happy. Except for one thing. Feel free to plug it in your calculator what the log of negative 5 is. It's not going to be very happy. And the answer is, it's because I haven't quite told you the whole story yet. The integral of 1 over x dx is the log of the absolute value of x. So, for example, if you had, let's actually do this one. The log of, okay, so the integral of, from x equals negative 5 to x equals negative 1 of 1 over x dx. Let's see. One-fifth to 1. It's going to look something like this. It's going to be some kind of area like this. Is going to be equal to the log of the absolute value of x evaluated from negative 5 to negative 1. So that's going to be the log of the absolute value of negative 5 minus, I'm sorry, the other way around, a log of 1 minus the log of 5. Now you have to put that in the calculator and figure it out. So they're nice round numbers. So the integral of 1 over x becomes that log of absolute value of x. And that's one of 3 laws that's showing you on page 601. But it seems like more of a thing to know what is the integral of the log of x dx. And that's the one that I always get confused. I was telling you before about that x versus 1 over x dx and all that. I always get confused. The integral of the log of x is one of those things you just can't memorize. Well, you could, but I don't. Is x log x minus minus x plus c. X log x minus x plus c. So, that's one of the ones, I am way too dyslexic to get that one straight. I have to always just look that one up. So, for example, let's say we had the integral, how about from 1 to e of the log of x dx. I mean, if we had a graph here, you know, your log function looks something like this, and we'd be talking about this area over here. We know then that the integral of this is x log x minus x evaluated from x equals 1 to x equals e. So that's going to be e of the times the log of e minus e minus 1 times the log of 1 minus 1. And then it's simplification. I'll leave that to you. I mean, there's all kinds of things that are going to cancel out, like e log e and 1 times log 1 and stuff. There are all kinds of things that are going to go to 0 here or cancel out and so on. But that's just like algebra. So you got that one. More generically, I mean, we love natural logs, like that one right there. But we don't always have a natural log based e like that. Sometimes we're talking about the log of just any arbitrary base, which I'll call b. Most of the time, of course, that would be log base 10. But it could be any old thing. And it's practically the same thing, actually. It's x over, oops, I better make sure I have that one right. X over the log of b. What? That can't be right. Hold on. Natural log, okay. Natural log of b times natural log of x minus 1. Anyway, that's also on that same page, whatever, that's 601 or whatever. It has that same example right there. All this is that change of base formula that you learned in like pre-calculus. So that's a big deal. All right. Again, then they're just problems. So the good news is this assignment is mostly just using something you've already been working on learning, namely that method of substitution. And so for today, starting on page 605, I want you to do 321 to 341 odd. And then there's a couple of assorted ones along the way. I'd like you also to do 355, 361, and 365. These are all just applications of those couple three rules that we learned along the way about integrals of exponentials and integrals of logarithms, and then they have they all have like substitutions in them. Really more exercise on substitution. All right, well that's no big deal. You'll have that done in no time.